Let's talk about ancillary equipment for hydraulics. So essentially, ancillary equipment is everything that isn't the pump, isn't the actuator, isn't the DCV, isn't even the hoses. It's kind of the stuff that's a little bit in between. Not the valves either. It's the tank and a bunch of other things. Let's take a look at some of the ancillary equipment. So essentially the oil tank itself. I guess the oil itself is an ancillary equipment. I don't actually know. I shouldn't have said that because I don't know. Right? But I mean, when the oil goes in the tank, I guess it's ancillary. But essentially the ancillary equipment is stuff that isn't the main components of the hydraulic system. It's all the kind of the supporting components. So coolers and heaters, for sure, definitely. Filters are ancillary equipment. And then the actual cleanliness code. We're going to be talking about cleanliness codes because it's so very important. Like when I get to that point in the lecture, you're going to realize how actually important cleanliness of your hydraulic fluid is. It's like paramount and huge. Okay, I will go on. Yeah, accumulators, really cool things, and we're just going to touch base on some measuring devices that you already know. So let's just move on and jump into some things. Here's some pictures of some stuff, ancillary equipment. These are filters. There are lots of different kinds of filters. We're going to find out that the hydraulic system has got a lot of really complicated filters in it, and there are many, many filters for many reasons. There's the tank itself. It's huge. A tank is like a huge part of the actual hydraulic system. It's very important. This is a cooler, which is really important as well. This is another cooler. This is a liquid cooled cooler. And this is air cooled. So we're going to take a look at those. So let's kind of start with talking about the tank and move on to all of those other things we looked at. So the tank. What does the tank do? It holds the oil. It's also a place for the oil to return, right? I mean, it's different from pneumatic systems, as we remember from pneumatics. The tank is the atmosphere. So essentially, in this case, the tank is a place for us to recycle the fluid too. We do a lot more than just hold the fluid in there. We recycle the fluid, we put it in there, we clean it, we condition it, and we cool it. In some cases, we actually heat it. And it's a really good place to allow the sediment, all of the particulates that are actually in the oil. It's a good place for us to filter those out and stop them from getting sucked back up into the system as well. We allow air to vent out. There's a lot of air, well, not a lot, but air can get into the fluid itself. And the tank, there are some components in the tank actually that can really help to remove the air out of the fluid. And it's also a place to put put the pump. So in some cases, pretty common actually, you'll see the motor, the prime mover, and the pump itself sitting right on top of the tank. So this is like kind of the interior of the tank, what it actually looks like. Now a tank is going to have a sloped floor. It's going to have a baffle in it. I don't think there is a tank out there that doesn't have a baffle in it. Some tanks have diffusers, some don't. And what's going to happen with the diffuser is that the diffuser is going to actually take that air or the foam, sometimes there's foam in the fluid as well. It's going to take the foam and the air out and it's going to allow it to diffuse up to the top. And what's going on is that this baffle is going to keep separate the actual material that's going in and the liquid that's going to be sucked out. So essentially, this baffle in between allows any particulates to come down here, settle in the tank, and then it's going to get sucked up here. Now, the interesting part of this picture here is the fact that this return line is close to the bottom of the tank. It actually doesn't really matter where it is, although it has to be below the fluid, and I'll talk about that in a minute. But the other is that the inlet or the suction tube has to be not too close to the bottom, but also not so far up that it's going to be sucking up air. So it's got to be in the middle. It has to be absolutely below the fluid level. So we've seen in both cases, the fluid has to be, the tube has to be below the fluid level. For the return line, the reason it has to be below the fluid level is because the return line in the whole hydraulic system is actually got to be full of It has to be full of fluid all the time. So the return line coming out of your DCV going into the tank, or the return line coming out of any component at all going into the tank, pressure relief valves, lots of things, has to be full of liquid all the time, because those things temporarily open and close, and they essentially allow the hydraulic system, often at low pressure, to act, sometimes at high pressure too, but to access the drain line. If there's air in the drain line, if that drain line doesn't go below the fluid level, then there's going to be air in the drain line, and that air is going to get sucked up, or it's going to get into the system somehow. So we got to make sure that our drain line is below the fluid. Pardon me, the return line. I said drain line, which is actually something else. Now this picture doesn't show a drain line, but I think you guys know what a drain is, and this is just kind of a side, that the drain is another line that comes out of some components that has just a few kind of trickles, just a little tiny bit of liquid will come out. Like in spools that move back and forth, liquid gets stuck around either side of the spool, and sometimes it has to just vent out of the system or out of the valve itself. There are other drain lines in other valves, and that's actually a separate line that goes back to the tank. That drain line actually doesn't have to be under the liquid, although it is, but it doesn't have to be. It's not as important for it to be under the liquid as the return line. The drain line is just often just little trickles of fluid that end up in the valve and end up having to vent out somehow. There you go. So the diffuser, we know what the diffuser does. The baffling is really important. The tank floor, it's typically sloped, and the suction line. So we've talked about all of this. Let's just move on. So there are different tank configurations. And there's a pretty standard tank configuration or conventional configuration where you're actually going to see the motor, the prime mover, and the pump right on top of the tank. But then there are other ones as well. And they actually have a benefit of the ones that are below the tank or beside at the same base as the tank. The pump doesn't have to suck the fluid in. So it's just a little bit better, I guess, but it doesn't really matter. Typically, this is used because of the form factor and also the accessibility to the pump. So you can easily access the motor and the pump, seeing it's sitting right on top of the tank. So you'll see that typically where most common is going to be right on top of the tank. Tank sizing. So important factors in tank sizing. You have to be able to change the fluid, right? So changing fluid level due to system operation. So what's going to happen is that as the system is being used, the fluid is going to go into a cylinder. Say you have like 3 or 4 cylinders and they're all extended. All of that fluid is now going to be in those cylinders. So you have to make sure your tank is large enough to accommodate all of those cylinders fully extending and sucking up all of that fluid, and the fluid level also being high enough that that suction line is still well below the fluid level. So it's important to be able to size a tank. You have to make sure that the tank is, there's a sizing method for this, but we'll go on. Looking at the environment inside the tank, we have to make sure that that environment inside the tank is separated from the outside environment. So the tank itself is protecting the fluid that's in the tank from the outside environment as well. And you know, lots of things can get in there, and we'll take a look at how we filter the fluid going actually into the tank. And then there's a lot of heat that's generated by the fluid. So, you know, I think you guys understand that we have a lot of pressure losses in a hydraulic system. When the fluid's traveling around, we're losing pressure, but that means actually we're losing energy. Or more specifically, there's energy going into the heat. There's energy going into the fluid itself. So the pressure loss is actually, there's energy getting sucked out of the pressure, and it's actually put into heating the actual fluid. So the fluid ends up getting hot as it comes out of the hydraulic system. It ends up getting really hot, especially with motors. Motors actually heat up the fluid quite a bit because they're turning all the time. The fluid's going through all the time. Actuators, they suck in and then extend and suck in and extend, and there's a certain amount of heat generated there, but certainly motors generate a lot of heat. So we got to get rid of that heat. Hydraulic systems, the oil, you know, it can actually expand as well. So we have to make sure that our tank not only has the ability to handle all of this fluid that's leaving going into the system and still staying high, but we also need enough space in the tank for the fluid to expand and for that foam to be generated on the top, which does happen. So we have to think about all of these considerations when we're actually choosing a tank. Essentially, as far as like sizing a tank goes, what you're going to do is you're going to take the maximum flow rate of liquid that's going to go out of that system. So if all actuators are running at full speed and there was a motor going, you calculate the gallons per minute and you take that and you essentially multiply it by at least 2 or 3. That's your tank size. And there has to be, I mean, any tank will have a certain level where you say, okay, fill the tank to this amount. And it's going to allow for space above that for the tank, for the fluid to expand and for some foam to be in there. So when the hydraulic system is running at maximum, the fluid of the tank will cycle through. So, all of the fluid in the tank will cycle through the whole tank within maybe like 3 minutes. Smaller tanks, like I think you guys know this, but I'll tell you this anyway. Power steering pumps, it's just a hydraulic pump. Actually, I've seen applications where people have taken power steering pumps out of vehicles and actually use them as hydraulic pumps to drive hydraulic actuators. But the thing there is, the tank is very, very small. It's just a tiny little thing. Although the hydraulic pump itself, I mean, the mechanism for the steering mechanism doesn't actually use a lot of fluid, doesn't use a lot of oil. But I mean, that fluid is circulating quite a bit. So as you're using your steering, that, I mean, if you were to constantly steer, I think all of the fluid in that little tiny hydraulic tank that's in there would be used within, 20, 30 seconds. It's really small. So sometimes the tank is a little bit smaller, but typically we want to make sure that the tank is at least 2 up to 3 times larger than the maximum amount of flow rate that's going to come out of, that's going to be required for your system. Coolers. So coolers are really important. Like I said, there's a lot of heat that's being generated in that fluid, and we put coolers into the system. And the coolers are going to be on the return line. So that's where the fluid is coming out of the actuator or the system, or after the whole thing, all the fluid's being used. It's being heated up, going through all the valves and the throttle valves and the whatever valves, going through the actuators, and collecting a lot of heat. And then as it goes back to the tank, before it goes to the tank, we cool it. The symbol for a cooler looks like this, and there are different kinds of coolers, and we'll talk about that. So essentially, so as pressure increases, so does temperature, and that comes from our the general gas law, PV equals nRT. We didn't talk about what this N is when we were studying that in pneumatics, but essentially you don't have to worry about that. You just have to understand that pressure and temperature, if the pressure increases, then I'm going to have a temperature increase. Also, if I lose pressure in the system, that's actually where a lot of the temperature is generated. Essentially, what's going on is that as the fluid is going through here, through this line, through the DCV, through the actuator itself, I'm going to be losing pressure. The energy there is actually put into heating up the fluid, and that's why I have so much fluid. That's why we have so much heat. So we have to put coolers in. So pardon me, I said have to. In some cases we do, in some cases we don't. It's all about application. It's all about, hey, you know what, is the pump burning out? Not the pump, pardon me. Is DCV burning out? Is there a motor being used and it's burning out? You have to understand that heat is a real problem in a hydraulic system. And sometimes it'll actually damage components. I think the largest thing we will talk about is contaminants. That's the biggest deal about what blows all hydraulic components. But heat is like a really big deal. So if your system is warm, if you can touch a pneumatic actuator or a DCV and you feel that it's warm, like this really warm, you got to cool that down. So although that heat goes into the fluid, which goes into the tank, and then the tank sits there. If you are only using the fluid intermittently and you're giving it enough time to cool down in the tank, you don't need a cooler. But if it's running all the time, often you're going to need a cooler on your system to cool things down. Now, there are a couple of different kinds of coolers. There are air coolers and water coolers. Yeah, that's how serious it is. They've actually designed 2 of these. Obviously, water coolers are much more efficient, and they look like this. It's pretty cool. So that's the symbol for a water cooler, and you can see the difference between an air cooler and a water cooler. Air cooler has it's the symbol of the fluid that's going in is not filled in, so it's just air. In this case, it's solid, and that's fluid that's going in that's actually liquid. So in this case, the fluid going in is air. In this case, the fluid going in is a liquid. So yeah, that's a really cool, typical water cooler. And then what's going on is that the fluid itself, the hydraulic fluid, is going to go in and out of these tubes itself, and the water is going to flow through here. The water is going to flow through here. Now, this is a cutaway, but you can see there's a pipe here with a thread on it. So the fluid will be flowing through here and going to a heat exchanger and getting recycled. In some cases, in really old factories and stuff, what they would do is they would just cycle water through there and then just dump it down the drain. It's terrible, but I mean, that's how it was. There are actually some air conditioning systems that are still like that in the city of Toronto, where they actually take water, city water, and just cycle it through a heat exchanger and then cool the house off, and the water just goes out in the backyard. I'm not sure if they use those anymore, but I remember seeing a few of them back in the 90s that were still around. Crazy. Heaters. Well, there you go. This is a symbol for a heater. As you can see, it's opposite from the symbol for a cooler. And heaters are important when we're starting off with cold hydraulic fluid. As you know, the hydraulic fluid is going to warm up. So I guess maybe in a really cold environment, like in machines that are working up in the Arctic or something, or way up north, or really just in Canada. So yeah, unless you have a really cold environment in a heavy equipment machine, where you're going to maybe possibly want to run the heater all the time. Because those heavy equipment machines, I guess if they have hydraulic motors that are running the tracks and stuff, I would imagine those hydraulic motors would heat up quite a bit because they're doing a lot of work. But I'm thinking of stuff that's consistently kind of running. You know, those excavators or whatever big heavy equipment and machinery, those cylinders are going all the time. So that motor is being stressed. It's actually the motor itself, not the motor, the pump. The pump itself is heating up the fluid to some degree. Yeah, so it could be that there's a lot of heat generated there, enough that it's just keeping the fluid warm during operation. But when you start those things up, often the fluid is really, as it gets colder, it gets really thick. So you want to heat it up. You want to make sure that the fluid is hot. And you know, the best way ultimately to heat up your fluid after, if it's really cold and you've turned the heater on and you've let it warm up the fluid, the best way to warm the fluid up after that is just to run the machinery kind of at a light load continuously for a few minutes, and that's going to warm the fluid up because it's going to circulate the fluid. And you also have to remember that if you were to say start an excavator up or some machine that's out in the field and it's really cold, all of those lines, the fluid in there is also really cold and really thick. So you want to circulate, you want to pump all of that fluid through there to warm it up and get it going through, put it through many cycles. But you don't want to stress it. You want to do that under a light load. Just like you would when you heat up your car, you know, when it's a really cold day and you want to get your engine running and your transmission running and your bearings going and everything else. You start your car, you let it idle for 30, 40 seconds or whatever, and you put it in gear and you just drive it really slowly for the first few minutes to get everything warmed up. And that's exactly how you're going to deal with a hydraulic system as well that's going to be cold. But if you need to have a heater or service a heater, this is going to just be threading right into the tank, and that's the symbol for that heater. So essentially, there you go. So let's talk about filters. Now, filtration is like huge, like it's really big. It's actually huge. The reason filtration is so very, very important, filtration is actually probably the most important part of a hydraulic system, period. And the reason is because 80% of hydraulic system damage can be directly tied to contamination. I'll tell you a story. Let's talk about a gearbox. Let's be mechanical engineers for a minute. So we're talking about a gearbox, and in the gearbox there's some gears and there's some tank. There's the fluid in the tank, right? It's some kind of, it's not a hydraulic fluid, but it's a gear fluid, gear oil, and the gears are spinning in there, and the gears keep blowing, right? So the operator keeps blowing the gears. I mean, whatever, the bearings keep going. And he's thinking, why? Why do the bearings keep going? What's going on? And this machine, is there downtime? I got to replace the bearings. It's costly. It's extra work. It's a real problem. What's going on? And the bearings are fine. The mechanism's good. They paid a lot of money for the gearbox. Well, the problem is the fluid. Now, the actual bearings were designed to be able to handle a certain amount of contaminants, or more specifically, the bearings were designed for a cleanliness factor. Yeah, I've got several slides just on cleanliness factors. Yeah, actually really very important. So what's going on is that because those bearings are working, and the tolerances inside the bearings are just several microns, like 5 or 6 or 7 or 8 or 10 microns. I mean, tiny, tiny. And some of those particulates that are in the fluid can actually be quite large. And as soon as they get in there, they can do a lot of damage. So that's a story about a gearbox. The best way to make sure that gearbox is kept well and maintained well, and the bearings are always going to work and they're not going to run out, and then ultimately you can get some vibrations in there and some real damage that can occur to a gearbox with dirty oil. It's just clean the oil. There are lots of different ways to clean oil, and let's just talk about that. But it's absolutely crucial to make sure that the contaminants in your oil are as low as possible. We'll talk about where some of those contaminants come from. But this is a general symbol for a filter. This is a hydraulic symbol and also a pneumatic symbol for a filter. It's got a dotted line down it. There you go. So it's really important that you make sure that you maintain these all the time. Let's take a look at a few different system filters, and then I have a picture where we can kind of see the whole thing, and we can see where all the filters go. There are these inline filters, and they're actually on the pressure line themselves. They will clean out the smallest particles. They'll take out the very, very tiniest, smallest particles. And the reason is because they're under pressure. So essentially what's going on is that you can have those with the finest filter. So these other things can't handle really, really fine filters because it's hard for the fluid to get through them. But an inline filter is going to be after the pump, and the fluid going through is going to be under pressure. It's going to be really pushed through. So you can actually put a very fine strain in here and collect a lot of the dirt. But ultimately, the best place to get the contaminants out of your fluid is in the tank, right? The best place to do it is in the tank, and we'll talk about that when we talk about kidney filters. Anyway, there you go. So return line filter, that's important. What are you picking up from the return line filter? Well, the contaminants that are put into the system from the actuator, from the motors, from the valves, from all of the components that are there, there's going to be some wear, right? There's going to be stuff, that little tiny microfibers of metal that fall off those materials. There are going to be little bits of seal that are coming out, that are going into the fluid and going through. So the best thing to do to get rid of that stuff after it gets put into the system through the actuators and the whole system itself, the valves and everything else, is just to, before the fluid goes into the tank, just grab it and say, hey, no, you're filtering it out. So this is an inline filter or a line filter, and it's on the return. And then here, a strainer. So a strainer filter is actually physically under the fluid in the tank itself. A strainer filter or a suction filter, is going to be at the end of the hose or the end of the pipe that's gone down into the tank, and it's completely submerged in the tank, and it's designed to pick up really much larger contaminants. You'll be able to pick up smaller pieces. They'll go through this thing, but then they're going to get picked up through this. But ultimately, again, like I told you, the best thing to do is just keep the fluid clean, and we'll talk about kidney filters in a minute. We should do that. Now, this strainer or suction filter is, again, it's underneath the fluid in the tank, but you can also get a suction filter that's external, right? You can have two of these suction filters. You can have a filter that's inside the tank, or we call it a strainer, and it's in the tank, and then we have an external suction filter as well. But usually you'll see either one or the other, and this will be outside the tank. There you go. So, and then we've got breathers. Breathers are really important because essentially, a couple of things I guess that breathers do is they allow pressure not to be built up, air pressure not to be built up in the tank, because air is in the tank, on the top of the tank, and that air is going to get warm. It's going to want to expand. It's going to want to get out of the tank. So you want to let it out of the tank. So a breather allows air to get out of the tank. Now, the other thing is that when that foam that's in the tank decreases, cools down. When the fluid cools down and it contracts a little bit, air is going to have to get into the tank. So we have to allow air to get in and out of the tank easily without any pressure differential. We don't want to create a vacuum in there. Certainly, no, we don't want a vacuum in our tank at all. You never want a vacuum with hydraulic fluid, period. There you go. So you're going to put a strainer on the top of the tank, but you also want to filter that because it's sucking in air, right? Not a lot, but air gets sucked in and blown out, very, very, very small degree, but it does have to go in and out of the tank. Well, air's got dust in it. It's got dirt in it. It's got stuff in it, right? It's even got water in it. We want to make sure that we can get rid of that the best we can. So strainers are always going to collect air at the bottom. Sorry, strainer. Breather. Breathers are always going to collect air from the bottom, so the air is going to go up this way. And that is so if there's water in the environment, like, well, maybe you might see these. Actually, you'll see these in rain for sure on heavy equipment or whatever. Although the tank is going to be in the cab, but there's still going to be water maybe splashing around or whatever. But water generally goes down and not up. So that's why these things are underneath here. So we don't want to get water in there. If it's splashed around, it's not going to get up in here. And yeah, there's just a certain amount of filtration in there. It's not a lot. It'll be like kind of a, just like a mesh, just a metal mesh or even a cotton mesh. Something that is just going to be just like a breather in the pneumatic systems, where we were talking about breathers in pneumatic systems. Where actually I've seen these that are fiberglass, and there's a fiberglass mesh that's in there. So essentially, it's easy just to replace them. Often you just grab a new breather and you just put it in, but some of the breathers you can take them apart and actually change the filter material that's inside there. Let's continue on and take a look at all of the different places that we may find some of these, and we'll talk about a kidney loop. So essentially what's going on here is that we've got my suction filter, which is here, and the suction filter is either inside or outside or both. And then we've got our pump, and then we've got a pressure filter. I mean, if there is a need for a pressure filter, we don't always see pressure filters. Pressure filters actually will steal some of the hydraulic pressure from the system. But again, they work really very well, and you can take some very small particulates out of the fluid. There's a return filter, very important return filter. You should always have a return filter on your hydraulic system. And I'm going to talk about two different kinds of return filters. One is just a standard return filter that we just looked at over here, where our return line filter is going to be like this. And but there's another one there that actually takes metal particles out, which is pretty cool. Now, let's talk about kidney loops. What a kidney loop? Kidney loops are huge. You should, not always, but whatever. You'll see a kidney loop somewhere on a cart somewhere, either on a cart or this guy over here has got some feet on it. He can just get picked up and carried around. You just plug this thing, you turn it on. So you take this hose and you stick it into the tank, and you take the exit hose and you stick it into the other side of the tank. And what it's doing is just continuously taking your fluid and cleaning your fluid out. Now, there's so many benefits about the kidney loop. If you're using an external kidney loop, and sometimes tanks actually just have kidney loops built right into them. Like this tank has got a kidney loop built right into it. So, but you can get portable kidney loops. And they're really good for gear oil, for transmission oil, for transmissions, for anywhere where you're keeping a lot of fluid. You want to externally clean that fluid. And they're also, kidney loops are really good actually for filling tanks. So for instance, if you wanted to fill a large tank and you had maybe a 5-gallon bucket of hydraulic fluid or any oil, gear oil, whatever it is, and you got to fill that into the gearbox, you got to fill it into the tank, you grab your kidney loop, you plug it in, and you put one hose in the oil, and you put the other hose into the tank, and you press play, and it just pumps the oil into the tank for you. But it also filters it, because it comes out of the factory, it comes out of the jug clean, but you want to make sure it's even extra clean. So kidney loops are good because if you use them for hydraulic systems in the tank, what's going to happen is that you're not going to lose pressure. So at any point, any filter in the system will steal energy from the hydraulic system. It's going to steal pressure. So in this case, you're not stealing pressure. Plus, the other thing is that you can operate the kidney loop at night or any time, any downtime during the downtime of the machine. You can put your kidney loop on and just, you can run it all night long, actually, and it really cleans the fluid. Again, your first line of defense for any hydraulic system is going to be the fluid. Keep the fluid clean. Tiny, tiny little particulates can really make a mess to all hydraulic components. Everything. It doesn't matter what it is. It can be a really big problem. So, yeah, and also dealing with flow surges. So essentially what's going on is that there's flow surges that going on in the system. So when you've got a hydraulic cylinder extending and retracting, all of a sudden the flow is going to be greater or less. And that means that any of these filters are going to be working kind of in a strange efficiency range. Filters actually work best at a particular flow rate. But if you're changing the flow rate up and down, the filter is actually not functioning as optimally, yes, as it could if it was just dealing with the flow rate it was designed to deal with. So kitty loop filters are good that way because it's just the flows, it's designed specifically to have a very specific amount of flow going through the filter with the pump that's on there, pumping it through, and it's designed perfectly to be able to do exactly what it needs to do. So kitty loop filters are a huge line of defense for your system. So I think I've convinced you now that filtration of a hydraulic fluid or a hydraulic system is the first line of defense to keep the health of that going. So here's just a typical filter here, and you have a paper filter that's going on, and the fluid goes down in here, and then it goes up into the middle, and it gets filtered out. Now I want to talk about this. It's a bypass check valve. It's important that we talk about this. The bypass check valve exists if the filter gets blocked. If the filter gets blocked, why would a filter get blocked? Yeah, because it's dirty and you haven't changed it. Yeah, it's really important to change them. So, and we'll talk about that. But what I'm saying here is that if it does get dirty, and if it gets full, the fluid is not going to be able to flow through it, and then it's going to be blocked, or it's just so bad that it's not flowing very well at all. We have a bypass. Now, ultimately, you never want to see the bypass on the filter flip. You never want to see that because you're going to be maintaining the filters. You're going to be making sure all of the fluid in the tank with the kidney loop, or just generally just maintaining and monitoring your fluid all the time and testing the fluid all the time, that this will never ever happen. But it's kind of a fuse in the system. What's going to happen is if the pressure is too high going through here, the filter is blocked, what's going to happen is that the bypass check valve, which is inside here, will actually open up, and the fluid is just going to flow right through the filter. It will not get fluid. It will not get filtered. And that is essentially just like, not like a fuse, because a fuse stops the system from running. An electrical fuse just says, nope, it's not running anymore. This will allow your system to still run. But if that happens, you want to run it only momentarily, just to at least extend or retract the cylinder, or to maybe run the system for a few more minutes until you can get a proper filter in, or just until the shutdown of the system can be maintained properly. Especially if you had a heavy equipment machine or whatever, and the filter's gone, you're like, okay, I got enough in here to drive it, to park it, and to lift it up the cylinder, lift up the excavator, remove it, or do whatever you have to do. But essentially, you do not want to operate a system if this check valve has gone. There are indicators on these things to let you know that the check valve has popped. So let's continue on and take a look at these. Spin-on filters, yeah, it's just a pretty basic concept. There's a spin-on filter, and that's how you change them. Suction filters in the tank are a little bit more difficult to change. You've got to open the tank up, you've got to go in there, you've got to get some gloves on, you've got to go down, and you got to get your hands dirty, and you got to undo that. It's also a spin-on filter, but typically a spin-on filter is a canister filter where you just screw it on. We'll take a look at this. Essentially, this is your indicator on how dirty the filter is. And I have another slide on this that's a little bit better than this, but we're going to talk about dirt carrying capacity of a filter. But let's just take a look at this spin-on filter. Now, oh, interesting. Look at this material. This material is metal. It's a metal sheath, right? So this is a suction filter. This is going to be on your tank. Actually, no, this is going to be a return line filter. It's not a suction filter. This is going to be a return line filter. And then what's going on here is that you've got this thing here, which is the filter mount itself. And then I'm going to be able to put the spin filter in here. So I'm going to put the spin filter in here. This is a return line filter. The fluid's going to come, return. It's going to go through here. It's going to go through this filter, and then it's easy to change the filter. It's just undo it and pull it out. It's not a big deal. So canister filters or spin-on filters are really very important. You'll see them in all hydraulic systems, and you just turn them in and pull them off really easily. So it's really very good advantage to have in the system. Now, let's talk about these contaminants. Again, I'm going to do a whole bunch of slides on actually different ways of measuring the cleanliness of the fluid. But essentially, it's important, again, to keep your fluid as clean as possible. But I want to talk about the dirt carrying capacity of a filter. The dirt carrying capacity of a filter is really important for your system because it has to do with pressure losses and energy losses and a whole bunch of things. So what's going on here is that the filter itself, right? If there are particulates in the filter, and there will be particulates in the filter because that's its purpose, that is its function. It's kind of a bit of a catch-22, right? So essentially any filter you put in the system is going to get dirty and it's not going to work as well, and then it will just, essentially if it's really bad, that check valve is going to open up in here and it's going to be a real problem. But the fact is, if you don't have the filter there, your system is totally destroyed and ruined. So you have to maintain the filters. You have to change them regularly. You have to monitor them regularly, and I will show you how you can monitor them in another slide. But for now, I just want to say that the dirt carrying capacity of a filter is really very important. You want to make sure that you overrate the dirt carrying capacity of the filter. So essentially, when you're choosing a filter, it will show you the dirt carrying capacity of itself, right? There are some other attributes to it that you can that we'll take a look at, but essentially, yeah, it's really important. And the dirt in itself, let's just say there's a perfectly clean filter. It's brand new. You just put it in. There's going to be a delta P. There's going to be a pressure loss through that filter. Work has to be done to put the fluid to go through the filter. And work and energy are the same thing. So if I'm losing energy, that's going to be seen in the pressure. So I am losing pressure across any filter, even brand new, right out of the box, right out of the factory, not a stitch of particulate in it or any dirt at all. There's going to be a pressure loss. And it will actually be rated on the filter. When you buy the filter, it'll show you a particular pressure loss at a particular flow rate. But my point here is that if it gets dirty, there's a greater and greater and greater and greater pressure loss to the point where it's so bad that a check valve is going to open up and the fluid is just going to flow through. So dirt carrying capacity of a filter is just the size of the filter. So you want to oversize it so that it can collect dirt because it's going to. That's its purpose and function. You want it to collect dirt. So making sure that it's as large as you want, because you know what? The best filter is the one that collects as much dirt as possible. But then that creates a problem because then it gets dirty and full. Oh yeah, just make it really big. So I hope that all makes sense. Beta ratio. The beta ratio of the hydraulic fluid is related to the efficiency of the filter? I guess that's important. Now let's talk about beta ratio. But before we do that, we're going to talk about magnetic filters. So a magnetic filter is essentially, you put that on the return line, it's going to be picking up all the tiny little particulates that fall apart. Actually, get this, the reason that those particulates end up in the hydraulic fluid with the actuators moving and the gears moving and all the rest of it is because there are particulates in the fluid. Yeah. So those tiny little particulates that are in the fluid, they get into the hydraulic system, they get stuck in between the gears, they get into the bearings of the gears for the motors, they get into the seals of the cylinders. When they're going through the valve, they tap, 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 tap under high pressure and flow. Those little particulates are smacking into the metal and they're tearing little pieces of metal off. So the cleaner your system is, the less damage is going to be done, and the less metal filings or particulates are going to be in your fluid, and the less you will need this thing. So this is going to be beneficial for certainly systems that have a lot of motors in them. Motors will generate the most particulates, metal particulates, because those gears are kind of meshing. There's extraordinarily low tolerance in those gears. They're just touching together. any metal that's stuck, any particulates in there is going to get crushed and is going to create a lot of force in there. It's going to rip off pieces of metal off of your gears. So, yeah, you want to make sure that you get all the metal particulates out. So that'll be on your return line filter. Plus, there's these drain plugs that you can get, drain plugs that have metal on them. And you know what? I was wondering about this when I was talking to somebody else about this. I thought, I wonder if they have drain plugs like this for cars that are magnetic. They should. Anyway, there you go. So, yeah, if anything, I'm going to pull the drain plug out of my car and I'm going to magnetize it. Okay, good. So, yeah, these things are good. It's like a filter, but it certainly helps to collect the particulates. Now, pressure drop, we're going to talk about pressure drop, and then I'm going to talk about beta ratio. So essentially what's going on is that there's a pressure drop for a filter, and they're rated for flow rate, and we can see that as the flow rate increases, the pressure drop increases. And I think that makes sense, right? As the more fluid you're putting through this thing, you're going to have a pressure drop. Now you can see this is these specs for any filter, and they're going to come from the data sheet from the filter for whatever the manufacturer is. For a Parker 5080T series spin-on filter, this is the flow rate pressure drop chart where you're going to see how much pressure you're going to lose for a certain amount of flow rate. So you have to take this into consideration when you're purchasing your filter, when you're putting this in. You have to know when you put the filter in, you're going to have a delta P. Now, this is what we're looking at here. I want to tell you guys that this is important, that on our external filters, you're going to see this. And if it gets into the yellow, that's it. If it gets even close to the yellow, change it. Dude, it's like a $20 filter. Like, whatever. It's going to save you thousands of dollars by changing that regularly. Again, it's the first line of defense. It's huge. So make sure you keep an eye on those things and never let them even get into the yellow. It's absolutely crucial that you don't do that. Beta ratio. This is something you just have to know about. I'm not going to ask you to calculate beta ratios or really wrap your head around it. It's just something that you will hear possibly, and you have to pretend you know what you're talking about. Right, so beta ratio is interesting. It's an interesting way of looking at the efficiency of how well a filter removes particles from the fluid. It's related to the efficiency, although it's not the efficiency. Let's take a look at some of these values. Essentially, what's going on is that when you have a beta ratio, there'll be a subscript and it'll be a number. And that number is the size in microns of the particulate that it's filtering. So essentially, there's a beta 25 and a 10 and a 3 and a 20 and a 10. So all of these are the particulates. Now, the beta ratio itself is the ratio of the fluid leaving or the fluid downstream to the fluid upstream. And I will show you that in another slide. But essentially, it's related to the efficiency, and it's not actually the efficiency. Now, the reason I think, and or some other people think, the beta ratio exists, as opposed to just using, why don't you just use the efficiency of the filter? I mean, efficiency is a pretty good concept, right? What if the filter is 99% efficient? What if it's 95% efficient or 92% efficient? Isn't that good enough? Well, yes and no. The beta ratio helps you wrap your head around values that are really close to 100%. In that, look at this. Essentially, what's going on here is that if I have a beta ratio of 2, it's 50%. A beta ratio of 2 is 50%. That's really, that's ridiculously low. That's not good at all. But if I go down, look at these numbers. If I jump up to 98.7%, the beta ratio is 75. Now, if I go up any higher, the beta ratio is going to get greater and greater and greater and greater. So what if I had, if I had 98.7%, that's really good percentage of filtration. But what happens if I got a filter that was 99%? 0.3% more. Well, the beta ratio is going to go up to like 150 or 200. If it was 99.5%, the beta ratio is going to touch 1,000. If it was 99.99%, the beta ratio is going to be like 10,000. It's going to be really, really large. So essentially, beta ratios are really good at showing you how well a filter filters beyond that 98 or 99% filtration. let's take a look at the formula and maybe wrap our head around this a little bit more. Here we go. Oh, by the way, this is a really good video. I've watched a few of these videos of this gentleman. He's got a PhD in fluid dynamics. No, actually not even of that, of like just fluid, I think. Not even fluid dynamics. Really, really smart guy. And he articulates himself well. 7-minute video if you want to know more about beta ratios. If you don't worry about it. It's not going to kill you. You'll never really need to know this. It's just, I need you to understand the concept. Okay, good. So I'm not going to get you to calculate any of this on the exam. But essentially, upstream and downstream, I think you guys are good with that term, upstream and downstream. So the upstream is the fluid going into the filter, and downstream is the fluid that's leaving the filter. So essentially, the beta ratio is the number of upstream particles larger than a certain amount. And I did say that subscript was for the value of microns that are larger, divided by the number of downstream particles, okay? So upstream and downstream. So essentially, you're going to get this number that's larger than 1, right? Because the number of upstream particles, the upstream, that's going in, and then number of downstream, this is going to be a very small, or it's going to be a smaller number, and the more efficient, or the better that the filter filters these particles out, they're going to be less and less of these numbers downstream, and this is going to be a larger and larger number as it gets larger. So there you go. That's the beta ratio, and you can just move on, and you know what it means now, and let's just move on and take a look at some of these values. Actually, no, sorry. We're still sticking with beta ratio. Just hold on for a second. Right, beta ratio versus efficiency. I like this chart a lot better because it really shows you the beta ratio and how it just jumps up. Essentially, at 50%, we have a beta ratio of 2, and then as we go down to here, 99, it's 100. So 99.2 is 150. 99.3, I think I said 99.4 was 150, whatever. And then as you go up and up and up, see these values are getting closer and closer to 100%. Oh, wow, that's really good. There's a big difference between 99.98 and 99.99. No, there's not. As far as percentage goes, it's 0.01%. Big deal. Actually, that's actually a really big deal for a filter. Interesting thing, you can look at a filter kind of this way. As you get closer to the speed of light, you know, the faster and faster you get, the closer and closer you get to the speed of light, you need more and more energy. So for me to get 0.1% closer to the faster speed of light, if I was 99% the speed of light, and I wanted to go from 99.0 to 99.1% the speed of light, I would need like 1,000 times more energy. I don't even know what the number is, but I think you guys might know that. As you get closer and closer to something, you have to put more and more and double and double and double. It's logarithmic. So essentially, what's going on, this is also a logarithmic value, or it's not actually logarithmic, but it acts like that. So if you look at this, as you get closer and closer, this gets like huge, like 50,000 beta ratio. So if you wanted to buy a filter that was 99.998% efficient, you're going to have to go find a filter with a beta ratio of 50,000. So there you go. That's the concept there. And there's some math that you can do with the beta ratios. I'm not going to ask you to do beta ratio math. Now you're good with beta ratios. You know enough about them. You understand the concept of why they exist. Let's talk about filter sizing. Okay, good. So I'm going to jump back to one of the other slides here because it's really important to talk about this. Again, filtration is so huge, I'm going to stop and do another slide on this. I've highlighted the word clean here. The flow ratings for a clean pressure drops. So essentially what's going on is that when you look at a filter, it's going to have pressure drop ratings, right? We took a look at that slide before. It'll have that slide where the pressure drop and the flow rate are looked at. And that's for a clean filter. It's for a clean filter. So you have to understand that filter is going to have at least that amount of pressure drop. So you have to understand that in your system, if you need a particular amount of pressure in the end at the actuator, you're going to be losing pressure through the lines, the hoses, the tubes, through the valves, through the DCV, through all of the components, and going to be losing pressure through the fluid, through the filter as well. So that has to be taken into consideration when you're when you're selecting all of the components as well as a filter. And then plan additional dirt carrying capacity for your filter. And I'm just going to go back to the other slide here where I was talking about this dirt carrying capacitor. Again, this is like the kind of the catch-22. You want your filter to collect dirt, but when it does that, it becomes inefficient. Well, just make it really big. So the larger your filter, the better. So always overrate, and you should at least overrate your flow rate by at least 1.5 or 2 times. So a filter will be rated to have or to allow a certain amount of flow to go through it. It will also give you the pressure drop for that flow. But essentially, wherever you have your filter, whatever it says, if you need a particular flow rate for your system, just double it. At least 1.5 times, or double the flow rate that's actually on the actual filter itself. Yeah, essentially it's going to be, the initial cost is going to be greater for a larger filter, but it's going to be hugely beneficial for you because your system is not going to break down. The cleaner your fluid, again, the first line of defense is the fluid itself. So much so that I'm going to do a bunch of other slides on fluid. It's that important. Yeah, I mean, you have to balance it as well. You can't put like this huge filter in there you're going to pay like $500 for, because it's probably not going to work so much. But the ease of also filter sizing, also the type of filter that you're going to put in, and where it's going to be located in your system. You want to put it as easy access as you can, and have it so that it's spin-on filter is always the best way to go, because it's just really easy to change it. So filter maintenance is huge. So yeah, factors to be considered: the type of oil, viscosity itself, the flow rate, the duty cycle, pressure, cleanliness required, cleanliness levels required. So we're going to talk about cleanliness levels. I'm going to do a few slides on this because actually it's really important. So all of these things are really important that you have to consider when you're selecting the filter. Now, most of you guys aren't going to be designing hydraulic systems, but it's good for you to understand how and why a system was designed and why there are more than one filter on a hydraulic system, and you're going to be able to maintain them, or at least understand why it's really important to maintain them. So there you go, that's really important. Now, again, I need you guys to really understand about fluid and about cleanliness. You really got to get it to the point where I'm actually going to spend some time telling you about cleanliness codes. Yeah, there are like this huge industry about cleanliness codes for fluids. It's huge, not just for hydraulic fluids. All these cleanliness codes are for all fluids, all oils, all gear oil, or whatever else that you're going to have. Cleanliness is a huge thing. So there are actually 3 different codes that are used, and or standards, pardon me. There's the ISO, the NAS, and the SAE. So I need to go through these with you guys so that you're familiar with the terminology, and you're also familiar with the fact that it's so crucially important. All of these particulates that are in the oil do a huge amount of damage. So let me just jump into the next slide here, and we'll talk about the ISO, which is the most common. But just let me tell you about components. When you choose hydraulic components, when you go and buy a hydraulic component, it will actually have a cleanliness code on it, or to it, or in the data sheet. It will say what the level of cleanliness code needs to be, or the minimum cleanliness code that part is designed to operate in. Now, I did tell you a story about that gearbox where the bearings are spinning and all the rest of it, and the clearances are just tiny microns. And the particles that are in there could be 15, 20, 30, 40, 25 microns. Well, if they're that big, they're going to get stuck in that clearance, and they're going to do really severe damage because everything's under high pressure and high force. So those things are going to damage, all those particulates are going to damage things. So a manufacturer will design something, and he'll say, hey, the fluid that goes through this, the fluid in the gearbox, the fluid in the hydraulic fluid, the fluid for the pump, the fluid for the gear, the fluid for the cylinder, the fluid, whatever it is, it will have a minimum cleanliness code on it. I need you guys to understand this. You can go look it up. You can grab your phone and whatever. If you ever have to need to know this, you can go look it up and review it again. But I need to show you guys, at least I need to talk about it a little bit more, and get you to understand that there are 3 actual different standards, and I want to explain how they all work so that you at least have some memory of what this stuff is all about. Here we go. So essentially, ISO is the most common, and it has to do with a range of particle sizes. So what's going on is that for a particular code, you're going to see a code like this. You're going to see a 17.13.9, and that'll be the cleanliness code on a particular part. Or if you go get your fluid, if you take the fluid out of the tank, which is a good idea, to take the fluid out of the tank and send it off to a lab, they will study it and they will tell you how clean your fluid is. This goes for gear oil, it goes for any oil, doesn't matter. There are labs out there, you can pay them money and they'll analyze your fluid and tell you how clean it is. They'll give you a cleanliness code back with your fluid. Either it'll be ISO or the other one of the other two. So this indicates this, essentially. Let's just bear with me, we're going to go through this. So it says that they're 17, 13, and 9. And this is the number of particulates, kind of. This is the number of particulates that are in the fluid that are a certain size. Okay, let's unpack this. So what's going on here is that the number of particulates are 17 that are above 4 microns. 4 microns is tiny. It's tiny. Okay, so so the number of particulates above 4 microns is going to be 17. The number of particulates above 6 microns is going to be 13. So they've measured this, or again, the manufacturer has put this code on their part or in the data sheet to say anything above these numbers is going to damage this. This component is designed to work on this cleanliness code. It's going to be 13, and then the 9 over here is 9 above 14 microns. So that's tiny. Like a micron, you know how small a micron is, right? Like a 25 micron is the thickness of a human hair. So it's really, really small. So what's going on here is that these numbers, 9, 13, and 17, are not actually the number of particles that are in the fluid. And we're actually looking at 100 milliliters of fluid. If there were only 9 particles in 100 milliliters of fluid, that would be ridiculously clean fluid. Like ridiculous, right? So let's take a look at what this 9 actually comes from. It actually comes from 2 to the 9th number of particles. Yeah, I know it's weird. I don't know where this comes from, but this is where it comes from. I have no idea why they did it this way. Deal with it. So essentially what we're doing is we're taking base 2 and we're putting the number of times in the exponent to equal the number of particulates that are in 100 milliliters of oil for a particular size. Again, we have these 3, and this above 17, sorry, above 4, above 6, and above 14. So in this case, if they measured in between 512, pardon me, and 1024, if they measured in between those two numbers, then they would give you a 9. Because that's above 512, which is 2 to the 9th. So they're going to tell you that it's a 9. And that's just, I guess it just saves them from using huge numbers. Like a 24 is huge. There's a lot of particulates. So if there are more than 16,777 particulates in 100 milliliters of oil, then you're going to see a 24 there. And that's going to be for these really small, like that's going to be above 4, right? Because that's counting all of the numbers. It's counting the small ones and the medium ones and the large ones. It's interesting. So that's the code, but it's the most common. It's a standard. So the ISO 1460 is a standard for a cleanliness code. You guys are experts on it now. You know enough to move on. You just got to know that this type of thing exists, and one day you're going to see it, you're going to hear about it, you're going to hear people talking about it. You're not going to be the guy that's actually choosing it, but you have to seem like you know what you're talking about. The next code over here is SAE code. So essentially, Society of Automotive Engineers, right? And again, like I'm telling you, this is a code used for fluids, all fluids, whatever, oil, gear oil, hydraulic fluid, whatever. So automotive engineers, the Society of Automotive Engineers, they came up with this standard. It's a common standard. It's used. You will see it on hydraulic fluid, used in hydraulic fluid. You will also find the ISO 1460 is probably the most common. We'll talk about another type of code, which you'll still see on older machines or older equipment. Yeah, this is the most current. Okay, so this is the kind of the newest standard that's come out of the 3 standards. And it's used in hydraulic fluid, and you'll see it. You'll come across it if you're dealing with a lot of fluids, and you'll see this. So this is a little bit. This is again, this is counting values that are greater than a certain size. So if you're taking a look at this, if the code itself is a 2, and by the way, there are 2 standards of codes within the AS coding. There are 2 standards of codes. So there's the MTF and the ACFTD. I don't know what these acronyms stand for, but there are 2 essentially different codes that are part of this. And you could see the coding. You could see a number 2. The coding, the cleanliness code on a particular part, or if you get your fluid tested and come back and they say, oh, it's an MTTD, it's an AS code, or they may see SAE code, but often you'll just see this AS 4059. You won't see the SAE, it's just AS 4059. It's actually the AS, get this, stands for aerospace. Yeah, I don't know why. Just fluid in space? Yeah, okay. Aerospace? I mean, it's not just space. It's airplanes and everything else, right? So the AS stands actually for aerospace. So you'll often see the aerospace or just AS 1459. So it may say MTD, AS 459, and the actual code is going to be MTD 2 or 3 or 5 or 6 or 7. Or you may see ASFTD, and then also it'll be a 2. But a 2 for ASATD is different than a 2 for MTD. Do not ask me why there are 2 different codes. Just don't do that. I don't know. Don't ask me what I'm supposed to know. I mean, again, it's just really, I don't know. I'm not a fluid, you know what? I understand fluid power, but all of this code stuff, again, it's not that important. It's just you have to be exposed to it so you remember this. I hope you remember something about what I'm saying. Anyway, there you go. So what's going on is that we're looking at a particular amount of particulates. So if it's a 2, if the code says, yeah, this is a 2, then you're going to have this many particulates greater than 2 microns, and this many particulates greater than 5, and this many particulates greater than 15, and this many particulates greater than 25, this many particulates greater than 50. You see how these numbers are getting up? And that 1 particulate greater than 100. So this is actually looking at the actual particulates, like the actual number of particulates. It's not the ISO where they're squaring it, the number of times you're actually squaring the base number 2. Or the exponent to the 2. It's not that. It's actually the number of actual particulates. So in this case, in 100 milliliters, there's going to be only 100 microns. That is huge. Like 100 microns, that's like a little thing, that's like a little chip of when you crack an egg in a bowl and you whip it up and you're like, oh man, a little tiny piece, and you pick it out, and you grab it, and you fight with it to get it out. That's like 100 or a couple hundred microns. That's a really, really big piece of contaminant. So there may be only 1 or 2 floating around. Anyway, so that's what's going on. That's what this is. So you can take a look at this example if you really want to know this a little bit more and read this. But again, this is just about getting you familiar with the terminology and the understanding how this works. Okay, good. So let's look at the NAS, okay? Again, the AS in this case is for aerospace. Right? That's really important. Fluid is really important for airplanes and stuff. That's really important. So, National Aerospace Standard, and there you go. This is fluid within a range, okay? So what you're taking a look at is fluid with, particulates or particles within a particular range. So, if we're taking a look at the microns over here, so if we take a look at a class 5, so if you see a part or any kind of hydraulic part, a pump or whatever, and it actually has a NAS on it. By the way, it's going to be before 2001. NAS has been around for a long time, since 60s or something. Yeah, 64. So NAS has been around for a really long time. It's been the standard like for 40 years or whatever. So you'll still see it. You'll still, maybe older guys will still talk about NAS. So you'll hear people talking about NAS. Again, it's not being used anymore. It's not the standard used anymore since 2001. But you guys need to know that it exists, because you'll still see it on parts, and you'll still see it in data sheets, and you'll still, I mean, you're not going to get fluid tested anywhere, and they're going to give you the NAS code. Let's just go through it. So essentially, what's going on here is that the class ranges from 00 to 12. So you're going to see a NAS, and you're going to say 00 to 12, and if it's a 5, then what's going to happen is it's going to have 496 particles in between 2 and 5. All right? So in between 2, so greater than 2 and less than 5. I'm not sure what happens if it's actually 5. Then I guess it can exist in either this one or this one. I don't know. I never really thought about that. So, but again, you guys don't need to be experts at this. You just have to know this is another type of code. Okay, I think you're sick of this. Let's move on. You don't need to know anything more about this. I'm not going to test you on this, but you just need to be exposed to all of this terminology. And by the way, I see a typo. That is supposed to be a capital L. Okay, good. So let's move on. Tank strainer. Okay, good. So we know what the tank strainer is for, and we know that the tank strainer is actually inside the tank below the fluid. And so when you see a symbol for a tank strainer, it's going to be actually physically in the tank. Let me just go back to another slide. So if you take a look at this, the tank strainer here, this is an external tank strainer, right? So that's actually going to be like this suction filter over here. It's going to be a suction filter, and that shows external. But you will also see them inside, and if you see it inside, you know it's a tank strainer, and it's actually below the fluid. So, yeah, that's the symbol for a tank strainer. The only difference is you'll see it in there. The thing I wanted to stop and talk about was this. I've highlighted this in red because it's important. They can deal with things, 74 micromesh wire mesh. It's a wire mesh. There's actually a physical wire mesh here, and then that's for the really big particulates, like 100 and 200 microns. Those really chunks. But essentially, this filter that's in here, which is just paper, it's going to filter up to 74 micrometers or microns of fluid or of contaminants. But now as I go on to a suction filter that is an external suction filter, so you're going to have this guy on the outside, and it is going to be better at getting more particulates. So it's going to be external, and it's going to be a lot easier to clean. So essentially, what you're taking a look at here, this tank strainer, tank strainer itself, it's not filtering a lot of particulates. It's not actually going to get dirty unless your tank is filthy. And if your tank is filthy, you got to go get a kidney loop and put it in there, or you just got to pull all the fluid out of there and just replace the fluid. So what's going on is that your strainer isn't actually going to get dirty because you're keeping your fluid clean, and all of the other filters in the system that are outside the tank are doing such a good job that your strainer doesn't get dirty. So you're not going to have to replace it. What you're taking a look at here is, if you're looking at a suction filter, which is an external filter, it is going to be filtering pieces that are a lot smaller, right? A lot smaller, to 25 to 283 to 25 microns. Now, let's take a look at this guy over here. So the pressure line filter. Now, as you can see, this is filtering out 3 microns, 40 to 3 microns. Really, really, really tiny particles. And the reason it can do that is because it's under pressure. Because it's under pressure, I can force, or the pump can force fluid through it, so you can make a really, really tiny, tiny, very fine mesh, and you can pull it 3 microns. That's like ridiculously small. This is the most efficient filter in your system, although the most effective filter for your hydraulic system is going to be a kidney loop. So yeah, you should have one. I mean, if there are a couple different hydraulic tanks in a plant or whatever, there should be a kidney loop filter, and you should have them cycling in all of them all the time. There you go. So what's going on here is I think it's important to have this bypass in here. So the bypass is important. It'll be inline. It'll be inside your filter. You'll have a bypass in the actual filter. But if you don't, you can just put an external bypass on there. And all this is just a check valve. But it's certainly good to have, because again, if that filter gets blocked and you still need to run the equipment just for a few cycles, it's important to be able to have that. Cool. Our return line filters, they're going to be down here as well. And also there's going to be a bypass on the return line filter, because if it gets blocked for whatever reason, you're going to want to make sure that the fluid can get past it. Now, these guys don't filter out as well because they're not under pressure, but they can be under pressure. Hopefully this makes sense. If I go up here for the pressure line filter, there's definitely, like, this is under pressure. Like, the pump is pushing fluid through there with a lot of force. But now let's take a look at this guy. If this guy does create some back pressure, which it will, because it's so small, if 5 microns is so small, it's going to create that back pressure. It's going to slow the flow down, and it's going to fight the fluid. But you know what? It's still going to be under pressure, like quite a bit of pressure. Let's just take a look at this. You might lose 100 psi or 50 psi across a filter. If it's really dirty, you're going to lose a couple hundred psi across it. But let's just say I'm going to lose 80 psi across this filter. Where does the 80 psi come from? The fluid coming out of the actuator, isn't it supposed to be like at 0 psi? It's just flowing to tank, right? Well, yeah, but the fact is there's pressure pushing it on this side. So therefore, there's this fluid over here. If it was blocked, large pressure would be generated on this side, right? So it is blocked by this, but only to a small degree, only to maybe 80 psi. Like I said, the example was this thing is actually stealing 80 psi from the system, and that's okay. It's like a pressure line filter in that it's on the return line, which actually will be under pressure if that filter itself says, no, I don't know, you guys, I need some of this energy that you're pushing this fluid through, and pressure will actually be generated on the upstream, pardon me, on the downstream. So the downstream from the cylinder is the upstream in relative to the filter. Let me just say this again. The fluid going into this filter is coming from upstream. It's upstream of the filter. And that is after the actuator, which is downstream from the actuator. But the actuator itself, in its retraction, will actually generate pressure, enough pressure, certainly 80 psi, not a big deal. I mean, it's going to make, and it's important to know this, guys, it's going to make your actuator inefficient. So if you chose that actuator, you're like, oh, I need like 3,200 psi to make that actuator do exactly what it's designed to do. Well, guess what? If there is a filter after on the return line and it's stealing 100 psi, this thing is going to generate, it's going to have less than 100 psi working. Actually, if you really want to get into it, it'd actually be less than 100 psi. What I mean is that if I were to find that this side was generating 100 psi because of the back pressure here, that would be seen on this side actually as higher pressure. It would be seen as higher pressure over here. So it would actually be more than 100 psi. And that's because of the different sizes on either side here. So if I wanted to generate 100 psi here, I'd have to actually put more pressure here to generate that. I hope that makes sense. I mean, that's not the point of this lecture, but it is the understanding that the pressure that's going to be dropping across here is going to be coming from the actuator, from the actual efficiency of the actuator. So when you're putting these filters in, and all of these components, every component you put in is going to steal pressure from the system. So you want to overrate everything. It's important to do that. I want to talk about accumulators, and then I'm going to let you go. So just bear with me here with the accumulators. Accumulators are really cool things. We talked about them in pneumatics to some degree. And they're used for the same reasons in hydraulics, although they work a little bit differently. They're mechanical. I mean, if you think about it, an accumulator for air is pretty easy. I mean, I even showed you an accumulator for air when I was doing my pneumatics lecture or whatever. I got one in the drawer over there. All it is just a tank, right? It's just an air tank. Now, the cool thing about air is it's compressible. So I can just shove more air in there and I can create, it's just a pressure tank. That's it, but it's small. And it's accumulator because air is compressible. I can shove more and more and more and more and more, and that creates higher pressure and more pressure and more pressure. I can't do that with hydraulics. Hydraulic fluid is not compressible. So accumulators are impossible for hydraulic fluid. No. But I mean, that might be your first thought. Well, how does it do it? Actually, there are 3 different ways that we can do it. One is that we can actually use air, because air is compressible, and you can put a bladder up here and fill it with air. It's pretty cool. So we'll take a look at the different types, and we'll take a look at some applications. So essentially, accumulators are available in a wide range of capacities, and they're actually measured in capacity. So when you go buy an accumulator, it's going to tell you the capacity of the accumulator, and that's all the information that's going to be there, just the capacity. Although it will also tell you the type. So there are 3 different types. Each type will just be labeled with its capacity, and there you go. That's the whole bit of it. We're not designing hydraulic systems to the point we're going to design the accumulator, but we're going to know that accumulators are needed, and we're going to take a look at some applications and why we may need an accumulator. There you go. So let's take a look at this. So energy supplement, to store the supplement energy. To deal with surges in the system as well. We'll talk about some surges, where surges can happen, and why you may want to be able to kind of supplement the pump. Just give the pump a little bit of help when it requires just an extra little bit. An accumulator is really good for that. Emergency power, same thing with pneumatics. We did one of the labs in pneumatics, and we talked about the fact that an accumulator is good. It can run the cylinder a couple times. In this case, an accumulator probably is just going to be used to retract or extend one of the cylinders, or move something, or just turn a motor a couple times. I mean, they don't have a lot of, you can actually get really large accumulators, but the thing is, their pressure curve goes down really quickly, much more quickly than, actually it depends. Whatever, just forget about what I just said, because it actually gets complicated when you get into different kinds of accumulators. A gravity-fed accumulator is the best at always applying the same amount of pressure. I don't need to tell you that stuff. You guys don't need to get into that, but it's pretty cool. Once you see it, I think once you see the picture of the different kinds of accumulators, I think it'll make sense. Shock absorbers. Oh yeah, for sure. I mean, there's going to be, it's like a capacitor in the system that's dealing with electrical surges in the system. It's definitely a very good shock absorber, and you can actually use them as shock absorbers. In that, get this, is really cool. You can put a hydraulic cylinder somewhere that requires that functions as a shock absorber, and you can just hook it straight up to an accumulator. It's pretty cool. Yeah, thermal expansion for sure. Like I said, like when the fluid gets hot, it expands. Leakage. Oh yeah, leakage compensation. I have to go through a coughing fit. I don't know what that was about. So leakage compensation for sure. Like, systems will leak, and you make sure that you deal with those leaks. And pulsation dampening. Yeah. So there you go. So accumulators are good things for all of those things. Let's just take a look at an application here. Like I said earlier, a gravity-fed accumulator, the symbol for that is just a square box on top of a tank with a line across it. In pneumatics, this is just an empty tank. It looks like this. And accumulator, and that's the symbol for an accumulator in pneumatics. In hydraulics, we put a line across it because it's sealed, because the fluid, it's not half fluid, but there's a certain amount of fluid in there. The rest of the accumulator has either a spring in it, it has a gravity weight on it, or it has a gas. So essentially this is a gas chamber, and you can see what it looks like here. That's the symbol for a gas chamber. I just want to go back to the gravity. This is pretty cool. I like gravity accumulators because they're always going to give the same amount of pressure, no matter how empty they are or how full they are. As we take a look at springs, as they get smaller or as they get used, their pressure decreases. Very much like an accumulator for pneumatics. As the air vents out, it's going to lose pressure. But in this case, the pressure is always going to be the same because it's gravity fed, and gravity is never going to change. It's pretty cool. So in this case over here, a gas, it's going to be doing the same thing as well. As the fluid is being used, the pressure drops. And essentially a gas is going to give you the lowest pressure. So if you wanted to be able to have this so it could deal with 3,000 psi, you're not going to choose one of these. You're going to choose a spring. It's actually going to be able to create the highest psi. So it's all about choosing the flow rate, the size. We're not going to get into all of the physics and the calculations for all of this. You just have to know how these things work and what they're used for. They're used for surges in the system. There's just an example here of of an example where there's an accumulator being used. A simple hydraulic circuit containing an accumulator that stores energy will be used later to improve to operate the motor when the hydraulic power is not running. So essentially, what's going on here is that I've got my motor and it's running and it's doing its thing. I can put I'll have another DCV on here on the motor, but however it is here, it's functioning. And in this case, for some reason, if the pump stops, I can at least jog the motor. I can jog it. I can run it just for a little bit, maybe to undo something or just to get it in the right spot so gears mesh up and I can pull things in and out or push things or whatever. So that's just a simple operation. Again, we looked at this in pneumatics. It was a very similar operation where there was a hatch. We had to be able to open the hatch and close the hatch once or twice, and we used an accumulator. So very, very temporary energy storage. Now, it's kind of cool. Talk about unloading for a minute. Unloading is a really cool concept. I'm not sure you guys really, if you talked about unloading in this course or not. But unloading is essentially an unloading valve. What it's going to do is it's actually going to allow the accumulator to take over from the pump. Or essentially, it's going to say, hey, I got it. Pump, you know what? You can just take a break. I'm going to unload you, and I'm going to take over. So the unloading valve itself is going to sense the pressure on this side. It's going to then open this up, and the fluid from the motor is just going to go whoop, right down, right out to the tank. It's going to give the motor a break. Now that can be that will happen when hydraulic press or when an actuator is working really, really hard. It has to work really hard, and you're stressing your motor. What's going to happen is that the accumulator is going to come in, and you can also have an accumulator dump where there's a valve that you can turn your accumulator on, but ultimately it's automatic. It's just going to happen automatically. Where the pressure here downstream is actually going to get low because the pump is too stressed. It's stressing the pump out. So the pressure is going to get low, and then this accumulator is going to take over. And it will take over, and as soon as the pressure goes low, it will take over and it will compensate. It will help the pump out, and it gives the pump a break because this unloading valve comes on. It gives the pump a break, and then it helps to actuate this. So there you go, accumulators. So you know a little bit about accumulators. You know why we might use them. You have a small concept about unloading valves, which are really cool. But there you go. You guys know enough about accumulators to move forward. There's no calculations or math. You just have to know the terminology. Cool. Some gauges. And more specifically, if anything, you know what a pressure gauge is. You know what a vacuum gauge is. You know what these gauges are. We studied them in pneumatics. But I just want to say the symbols. It's the same symbol for vacuum gauge. For hydraulics and for pneumatics, it's a V with a line across it. I was going to say an upside down A. I think this looks like an upside down anarchy symbol. I don't know why. It does. Anyway, there you go. So a burden gauge, typical, we studied this in pneumatics, a typical gauge. They're really cool the way they work. Actually, the differential pressure, the concept of a differential pressure in a burden gauge, is more so understood in pneumatics because we may have 100 psi, but the atmosphere is 14.7, and this is actually telling you the difference. The gauge pressure is going to be 100 psi above 14.7. Again, all Borden gauges are differential gauges, even in hydraulics. But that's the symbol, and then that's the flow meter gauge. And flow meters, you know what they look like, you know how they work, you've used them in the lab, and then you can get them digital. So there you go. And also the flow gauges as well. And that's just, again, the symbol for a flow gauge. And you guys are good. So there you go. So I've talked enough about ancillary equipment. I mean, you don't have to do any math. You just have to understand the terms. You have to kind of, just get an idea of all of this stuff. And I think probably one of the most important points is that your first line of defense is keeping your fluid clean. So you guys are good to move on to go into a hydraulic situation and be able to talk the shop talk and understand why a system may have 2 or 3 filters. And yeah, now you got a good idea of what's going on. That's it. Okay, bye.